Okay, guys, so today we are going to be analyzing two proton NMRs. There's going to be an NMR for ethanol and an NMR for ibuprofen, which is going to be the next structure. And so for ethanol and ibuprofen and for any NMR, it is really nice to be able to organize your findings in a little table like this. So you're going to have your number of signals, position, integration, spin-spin coupling, and a guess of the partial structure that you think it might be. So we're going to start at this number one signal, which is going to be the furthest downfield. So furthest downfield is to the left of 2 ppm, and then to the right is more upfield in regards to the signals on this NMR. And so the one that's the furthest downfield, all the way at about 3.7 ppm-ish, which we can write down for the position, is going to be the first signal. And that has an integration of 1H, which is given to us. And usually these things are going to be given, or else you can use a literature IR spectra, or you can use a literature NMR to compare the integration values that you need. And for the spin-spin coupling, this looks like it is a singlet because there is one peak for that specific integration. And a guess for this particular structure would have to be an alcohol group because of the 1H factor and the fact that it is a singlet. Also, the fact that it is around 3.7 ppm leads us to believe that it is an alcohol group. If we saw this on an IR, it would be a broad, long, strong curve. But anyway, since it is a singlet, that means it has no neighbors. And to find the spin-spin coupling, you do neighbors plus 1. So this leads me to believe that it is an alcohol. Now, for the second signal, we can see that this is also kind of around 3.7. I'm going to say around 3.5 ppm. The integration is 2H, which is again given to us. The spin-spin coupling is going to be what looks like a quartet, so 4 spikes there. And my guess for this partial structure would have to be, since the integration is around 2H, we know that it must be a CH2 group. Since the spin-spin coupling is a quartet, this means that the CH2 group must be near right next to a methyl group, because you would do 3, which is the neighbor, plus 1 is 4, which is a quartet. So we know that it must be a CH2 next to a CH3. And how I would know there's no other neighbors on the other side of the CH2, because since it is very close to the downfield area of the alcohol group, and there's the CH2 is going to be directly attached to the oxygen, there are going to be no neighbors on the other side of the CH2. Now to inspect the final and last signal of this proton NMR. This is way further upfield, so we know that it's going to be farthest away from the most electronegative atom in this molecule, which is the oxygen in the alcohol part. So this is around, I want to say 1.2 ppm. The integration is 3H. So I'm thinking methyl in my head. And then the spin-spin coupling is a triplet because there are 3 spikes seen. And so our guess for partial structure for this part would be a methyl group, because we can see that it is a triplet next to the CH2, which is predicted in above. And also it's 3H, which means it must account for 3 H's. And now, again, like, this table is very nice to be able to put everything together. So now when we come up to try to figure out what our final structure is, we are able to look all the way downfield, which we see an OH. So we're going to draw that first because that is the furthest downfield. And our next guess is going to be a CH2 next to a CH3. And so we know that is true because the CH2 must be next to the OH because it is really close on the proton NMR next to it. So what we're going to do for this is we're going to draw this as a partial structure, because right here you're going to have a CH2 that is right next to the alcohol, and on the end you're going to have a CH3, which is way further upfield and farthest away from the OH structure. So this is precisely how you find the ethanol structure using the proton NMR. In regards to degrees of unsaturation, that is not needed to be found here because um, ethanol does not have any rings and it is only has single bonds. So we are not able to find the degrees of unsaturation here. And next, we are going to deduce the structure of ibuprofen from that proton NMR. So for ibuprofen NMR, obviously, this is going to be a little bit more complicated. But so there are 8 total signals here. Some of them combine to deduce kind of one type of partial structure. But basically, I'm going to walk you guys through each part of this, and we're going to just talk about like what these partial structures could mean for the entire molecule. So for the first signal, this is positioned around 11 ppm, and the integration is 1H. I pulled this from a literature NMR spectra of ibuprofen to figure out the integral because we need that for each thing. This is also a singlet because there is one spike. And basically to analyze this first signal, this is going to be a carboxylic acid because most carboxylic acids are between 10 and 12 ppm on an HNMR spectra. So we know that it must have this structure, which is, I drew it up with the arrow. And then next for the second signal, this is second and third signals are both positioned around 7.3 ppm. They are 2 doublets and they both account for 2 H's. And so if we think about this, this is going to deduce a structure of a benzene ring. Benzenes usually show up around 6 to 8 ppm on the NMR. In the IR, you would see overtone in the graph. But here we basically can see it from this structure. So when you see these 2 doublets here, we know that the benzene must look something like this to the right under the guess column. It's going to have 4 H's on the sides. That accounts for the 2H plus 2H in the integration. They're both doublets, so they're going to be next to 2 H's. Or have 1H neighbor plus 1. And we know that the functional groups are going to be on the X side and the Y side. And basically, for this, the fourth signal is going to be around 3.6 ppm, and that's going to be a 1H in a quartet. So that means it must be an H next to a CH3. Signal 5 is around 2.5 ppm. That has an integration of 2H, and that's a doublet. So we must see that there is a CH2 somewhere in the molecule that is also further upfield. So we know that it's going to be farther away from the benzene ring. Because we are centering everything around the benzene ring for determining the structure of this molecule, we're going to compare everything to where the benzene is on the NMR. And then next we have a multiplet of 1H at 1.8 ppm. So we know this is going to be an H that is surrounded by multiple CH3s, multiple CH2s. It's going to be surrounded by many molecules. We can't really commit to a structure for this yet because we need to figure out the surrounding molecules first. Signal 7 is around 1.5 ppm. The integration is 3H and it's a doublet. So we know that it must be a CH3 and it is going to be next to an H. It's also going to be further upfield, so it's going to again be like pretty much away from this from the benzene ring. And then also the last signal is going to be at 0.5 ppm. It is the strongest of all of them. It is a 6H. And also a doublet. So we know that this must be 2 CH3 groups together because of the fact that they're coupled together, and it's also a doublet. And then we will continue to find the structure in one moment. So I also wanted to briefly talk about the relevance of degrees of unsaturation in the proton NMR. Again, it would be better if we could use all of the different types of ways to analyze structures, but I think it's really important to include degrees of unsaturation. So the formula is 2C plus 2 plus N minus H divided by 2. And so I calculated it here from the structure of ibuprofen, which I looked up. And so that's 2 times 13 plus 2 minus 18 divided by 2, which is 5. So the way degrees of unsaturation works is that it can either be a double bond, a ring, Yeah, it's either a double bond or a ring. So that's why it didn't show up in an ethanol, because this structure we know has a benzene ring. So we know we must calculate degrees of unsaturation. So we can see here that we have 5 degrees of unsaturation. So that means we could have a double bond like here. And we have the ring, which is going to have 1, 2, 3, 4. So the ring is going to have 4 and the carboxylic acid is going to have 1. So that's going to equal 5 degrees of unsaturation. So this just tells us how like the functional groups are going to be like it basically just shows us that we know that these functional groups are going to be here just because of the degrees of unsaturation. But anyway, basically taking a final look at our table here, we see that there must be a multiplet and we must be doublet and all these other spin-spin coupling. So to reveal the structure, which I drew down, the structure is, drum roll, is this. So to further analyze this structure here using the table and the NMR. So we see that there's a carboxylic acid, which is going to be the closest to the benzene ring. We also see that there's a CH3 and an H. And so this H is going to be the quartet that was seen here because it's next to a CH3 as seen. And the CH3 is going to be the doublet. So it's next to 2 H's here, or next to 1 H, sorry, plus 1 is going to be a doublet. So that explains the functional groups that are on the top. Again, we see the benzene ring in this formation with the 2 H's on either side. That corresponds to the 7.3 ppm for both signals 2 and 3 on the integrations of both 2H of the doublets. So we were right in predicting that. Also, obviously, since there's a benzene ring, we know that there's 5 degrees of unsaturation, as I pointed out a little bit earlier. Now to go to the bottom here, we know that there is a CH2 because we saw the doublet at 2.5 ppm. We know that is going to be the closest to the benzene ring because it is further downfield towards where the benzene ring is. So that was around 2.5 ppm. And then we know there's an H multiplet because right where the CH3s connect, there's going to be an H there because of that 4th bond. And basically, if you add the neighbors on either side, it's going to be more than 6 or 7, and we call that a multiplet. So again, we couldn't really deduce a structure from that multiplet, but we were still able to kind of figure out where the structure is based on the 2 CH3s that were there. And so at the end here, there's going to be the 6H, which is seen as the 2 methyls branching off of the center here. So we know that there's going to be 2 of those because they are doublets. So, you know, there's a 1H here plus 1 is 2. And since they are both doublets, we know that they must have been connected by a central atom or like molecule together. So we know that there must have been a 6H, 2 CH3s, which we kind of predicted in the guess. And then at 1.5 ppm, again, a 3H doublet that is seen up here in the final structure. So again, by using the tables here and degrees of unsaturation, we were successfully able to deduce the structure of ibuprofen. Again, if you continue to analyze the position of the benzene, again, using an IR would have been more beneficial. But if you're able to look at around 7 ppm and you are able to see the integration of 2 plus 2, and you're able to see 2 doublets that are very close to each other on an NMR, that is usually going to be the indication, again, of a benzene ring. And then also with that position, we know normally that with the positions of X and Y here, we know that those functional groups are going to be there. And those positions are based solely on the upfield and downfield placements of the NMR. If the carboxylic acid, which usually is furthest downfield, wasn't, then we would know to be farthest away from the benzene ring. But again, the carboxylic acid is always going to be between 10 and 12 ppm. So that is the final structure of ibuprofen. Again, a more complex structure. But this table is very good in, making guesses. And once you have the guesses, you're able to deduce your final structure. Thank you for your time.